This one's going to be interesting. A mutual friend actually told me about Alex quite a couple years ago about what he's doing, and is of interest to me as well for what I do. So he's going to be talking about advanced security analytics and what he's been doing within Telus. So let's give a warm welcome to Alex Loffler.
Thank you. Thanks, everyone. And first of all, I'd like to thank the organizers for BSides Vancouver for another fantastic year. I'm sure you agree it's been a fantastic year. Okay, so as I'm the only thing between you guys and a cold beer in the kind of fabulous Vancouver afternoon, I'm going to get cracking. So, what I'd like to talk to you about today is advanced security analytics. What I mean by that is how do we get past some of the issues that we have with current SIM technologies and some of our approaches. How do we build a more statistical approach and a more advanced way of detecting anomalies and badness in our environments as opposed to our simple if-then-else type rule sets. So why do we need this kind of thing? How do we respond? How we've looked at implementing some of this, and then maybe trying to ground it in a couple of use cases, and then a summary. So, perimeter erosion. So things like BYOD, Wi-Fi, telecommuting, mobile computing, all of these things are making it increasingly difficult to define the boundary of an organization. The rate at which we're delivering products and services is also increasing. So the complexity of these products and services, as well as the rate at which we're delivering them, is increasing. And a side effect of this is that the expected lifespan for each of these products and services is also decreasing. And as the expected lifespan decreases, so does the appetite for investing in the hardening and security posture of the individual products and services. So we're ending up in more of a Google beta rather than a 6.9 dial tone type of delivery model. Another catalyst for this is virtualization. So virtualization is designed to improve IT responsiveness and decrease cost, but you very rarely see security in that conversation anywhere. And some of these implications are kind of overlooked. So the ability to actually make changes at speed in an environment brings added risk of its own nature. So an innocent mistake at 2 o'clock in the morning could generate instantaneous changes with far-reaching consequences, never mind whether those actions are actually malicious in nature. Another concept that's introduced is the concept of monoculture. So in the old world, things like network, storage, and application tiers used fundamentally different technology stacks. Whereas today, a single vulnerability in that virtualization tier can cause massive potential impacts. And I'll spare you all of the stats from Mandiant and the Verizon data breach investigations report, etc. I'm sure I'm preaching to the choir on that one. So how do we respond to some of these new threats? Governance, of course, it's the knee-jerk reaction. It's the first thing that we go to when we see poor security posture in our environments. But unfortunately, this actually tends to do more harm than good. We end up bringing change control to a grinding halt. Existing BCPs are applied too broadly. Glitch in the matrix. We're good. And new policies are created in this flurry of activity, but are not maintained and eventually go stale. So this drives change underground. It adds complexity and cost, and it doesn't actually improve security. And in extreme cases, it actually undermines the existing security posture, as the official process becomes so arduous that it actively encourages this kind of concept of shadow IT, sidestepping the governance process altogether, be it the new or the old governance. But don't get me wrong, governance is essential, but it has to be applied or increased with care. So if stronger governance isn't the answer, what is? Well, controls. Let's add more controls. Today we have a vast array of security controls to choose from. The problem is that even implementing A small subset of these controls in anything but the simplest of environments results in complexity and overlap that's kind of reminiscent of some kind of Rube Goldberg machine. Most people think of an edge firewall as an example, as a simple, reliable, robust appliance. But what if our edge firewall contains a vulnerability? Do we put another firewall in front of that firewall? Well, actually, yes. For critical infrastructure, that's exactly what our industry does today. And we try and select a different vendor in the hopes that vulnerabilities don't overlap. And this basically doubles our operational overheads. How about that mouse over it, see if that works. Let's see if that's cool. Okay. Sorry guys, bear with me for a sec. Cool. Okay, so this firewall in front of a firewall kind of concept, and we just keep adding more and more controls to a core asset that's actually fundamentally broken to begin with. And we end up kind of justifying this whole thing with a horribly recursive version of defense in depth. So instead of applying third-party band-aids, what if we focused our efforts on actually building a secure asset in the first place? So our environments and our lives would become quite a bit simpler. So this kind of unicorns and rainbows version of the world would mean that we could kind of get rid of all security controls that focus solely on detecting and mitigating flaws in the technology stack itself. So kind of get rid of some of these bad boys. Which means we're left with a much smaller set of attack surfaces, or attack vectors, most of which are basically around access control and identity. So things like detecting credential theft and abuse. So we can now pretty much deploy a naked OS, web server, and web app and fully expose it to the ravages of the internet while maintaining a mathematically provable security posture, which would be fantastic. So this would mean we could reduce the provisioning lead time and complexity because there are fewer components to deliver, no false positives, things like WAFs, IPSs become a thing of the past. No overhead from agents on the box, HIDs, AV, all of that stuff kind of goes away. No resources required for maintaining these additional security controls. So this is all great stuff. But the problem is that building these kind of provably secure operating systems or provably secure systems costs a lot of money, a huge amount of effort. And really they're kind of relegated to mission critical type systems like nuclear power plant controls or flight control systems today. But if you think about it, it's a one-time cost. Think about all of the additional security overhead from a cost perspective that we expend as an industry or as a planet today. I would be much happier to spend $10,000 per OS instance instead of $50,000 on all of the controls to try and secure that OS. Okay, so meanwhile, back in the real world, how do we actually respond? So we have to deeply accept that we're never going to keep 100% of the attackers out of our environments. Actually, if you believe some of the industry figures, between 30 and 50% of attacks originate from inside a threat anyway, be that employees, former employees, contractors, or supply chain. So they're already within the walls. They hold trusted positions with valid credentials already in our environments. So we have to build a model that can fail gracefully. How do we detect this stuff and not be as brittle as the fortress mentality? Really, the only way to do this is try and move backwards in the kill train. Try and detect the attack behaviors before they actually get into our environments and cause damage. So in effect, build a bigger ear and place it closer to the ground, both in terms of telemetry data as well as threat intel itself. And from a threat intel perspective, we're starting to see a lot of interesting activity in the industry there. Things like Avalanche from the FSI site groups, things like CVSS version 3 that's, I believe, going to be ratified later this year, Styx, Taxi, etc., to allow us to start communicating and disseminating this kind of threat intel. The next piece is visibility. So a lack of visibility in the environment is really debilitating. It stops, or it doesn't allow us to detect or respond to threats in the environment. It stops us from being able to actually define internal security perimeters or zones of trust. And it also makes us completely blind to the ability to actually identify actors across an organization. And I'm using the term actors here in the broadest sense. So that could be employees, IT assets, network elements, customers, suppliers, attackers, anything that is active and actually can do something in your environment. So visibility requires telemetry. And Wikipedia defines telemetry as an automated process by which measurements are made and transmitted to receiving equipment for monitoring and analysis. I'm a bit of a Formula One fan, and it turns out that every Formula One car in a race will generate between 8 and 10 gigabytes of compressed telemetry data per car, per race. So the question I'd like you to ask yourself is, if a single F1 car can generate over 1 billion events per hour to a team of 8 to 10 people dedicated to monitoring, analyzing, and responding to that data in near real time, how does the logging and monitoring of your organization's critical assets compare? And how does it compare both in terms of acuity and depth of that log data, but also in terms of the resources dedicated to its storage, processing, and incident response? We really have a gap here as an industry. But even in the most poorly instrumented environments, there's an avalanche of data being generated every second. Huge numbers of logs, network, HIDs, human-generated, etc. Typically, 80 to 90% of the interesting actions in an environment are actually already logged today. The problem is that they're logged in places that are difficult to search. So the problem becomes moving that raw storage to a platform that's logically centralized and searchable at scale. So our platform is ingesting somewhere in the order of 4 billion events per hour currently. And we'll get into what we're doing with some of that data in a minute. But given the sheer volume of data generated by today's environments, the traditional approach of waiting for that one golden event that flags the badness is no longer viable. Building these if-then-else rules doesn't get you enough visibility. We need to take a more statistical approach to this. We need to baseline, we need to understand what normal is. Building rule sets is not scalable anymore. So the trick is to find a technology that's capable of ingesting, processing, and rendering this information in a cost-effective and timely manner. And it kind of sounds obvious, but the value of the analytics must exceed the platform's cost for this to be a viable proposition. So I believe we finally are seeing tool sets emerge that are able to scale to this kind of volume, while maintaining a TCO that doesn't void the business case, as it were. And unfortunately, the SIM industry as a whole has a lot of catching up to do with respect to these technologies. But we're seeing some glimmers of light here. We're seeing approaches such as ELK, which is open source, and the OpenSOC project, which I think is backed by Cisco and Hortonworks. So we're ingesting both log and packet data into the same repository. Our first tier, our ingestion tier, is basically based on a stream processing paradigm. We're using technologies such as Kafka, Storm, and Esper to do the actual processing here. So this is kind of our tier 1 processing. When we receive the logs, we're doing things like normalization, parsing, and enrichment of data. The next tier is, in effect, the MapReduce tiers, where the data actually hits disk for the first time. It's kind of our long-term storage, and it's where we do CPU-intensive batch-type processes against the data sets. So we're using components such as HDFS, HBase, and Hive. And then the final tiers basically allow human access to that data and allow us to build models onto that data set. And it's basically anything that can speak Hadoop. So currently we're using things like R, Pig, Splunk on Hadoop, which is called Hunk, unfortunately, Gephi, Multigo, Tableau, etc. Basically anything that can speak MapReduce into the cluster. So this approach allows us to combine the benefits of ingestion time pre-processing with search time schema application, which is critical to scale. So the ingestion tier, so as I said, we're using a concept called stream processing or complex event processing. And this differs from traditional RDBMS or message-based systems because they make temporal and real-time queries very difficult. They also typically generate a conflict between reads and writes. So a typical RDBMS-based SIM, you actually see an ODS or an operational data store which is responsible for reading the log data in, and then a reporting data store to actually service queries. The problem as the data sets get large is that the synchronization of these two data stores becomes really ugly really quickly. So instead of focusing on the data structures, building tables and relationships and then pouring that data into these structures, we instead focus on the flow of data through a topology of processes. So the example here is that we may have a syslog listener that then basically geolocates IP addresses. The other thing may be a filter for purely authentication events that then builds authentication sessions and then starts looking at brute force detection. So as you go from left to right, you're reducing the total volume of log data and you're increasing the value of the log data. So now that we have this data kind of pre-chewed, we have it normalized, etc., what do we then do with that? So let's pick a very simple example. Let's say I want to flag any possible indications of compromise by monitoring the destination of outbound web traffic. So I'm looking at my user traffic, I'm looking at Alex is going out to google.com, is this a good, or is this an indication of compromise? So a solution to this, a simple solution to this might be I might go out, try and grab as much threat intelligence about known bad IPs and domains in the world, and generate a blacklist. If I see a web proxy hit or I see web traffic hitting one of those IPs or domains, I flag it to my cert team. Simple stuff. Version 2 might be, well, a binary output may not be good. I may want to rank the badness of the event from a scale of, let's say, 0 to 100. Based on feedback from your cert team, maybe you start trying to implement whitelists because maybe some of your threat intel is incomplete and they're saying things like, google.com may be bad, so I want to whitelist certain domains. As I start building more and more logic into this, it gets harder and harder to maintain the code base. Version 4 might be, well, let's take a completely different tack here. Let's inspect the DNS registration dates for the domain that's being hit. And the assumption here is that, let's say, a production server, for example, has no business in talking to a domain that's less than 24 hours old. So now what I have is a bunch of models that are all running in parallel and some kind of combiner or some kind of way of weighting the outputs from each of these models so that I can make a determination as to whether I need to cut an incident or not. The problem with this is manually maintaining the logic for this combination process is not scalable, especially when you start adding hundreds of rules and potentially hundreds more models. So what we're looking to do here is use ensemble methods to do this, and a way of automatically generating a feedback loop to modify those weightings based on feedback from the cert team themselves. So we can exploit a user feedback loop to automate the tuning. So the ability to combine model outputs in an arbitrary way, such as weighted average, challenger champion type models, but also the ability to modify those weights based on the user feedback. So if the user tells me that, no, this is actually a false positive, this is not a bad domain, I can actually use something like Bayesian learning or naive Bayes learning to actually modify those weights. So over time, I'm selecting models that have performed well historically with respect to the feedback from the users. The other nice thing about this approach is that we can introduce new rule sets or new models at very low risk. So we introduce the new model with a weighting of 0, and the only time it would actually start contributing to the output is if it actually proves its performance over time, which again is very different to traditional sim tools where you add a rule, you can actually really kind of break the platform sometimes. Okay, so let's get into some use cases. So we can type. So the question that we asked ourselves is, are we able to use log and netflow data to be able to automatically classify devices based on observed behavior? If we can do this, then can we then flag statistically significant deviation from that baseline? So I'm not defining normal myself. I'm letting the system work out what normal actually is. I actually took this a step further and said, well, okay, if we can type the log data and then use the relative mix or ratios between log types coming out of a device, can I then group that asset and then classify those assets? So it turns out for this analysis, we don't even need to deeply understand or parse the logs themselves in the traditional sense. So I don't need to build parsers for a data source. What I can do is I can use string manipulation techniques. I can use things like n-gram analysis based on the fields, based on the character positions, to work out things like diversity for a particular field. If this is a timestamp, it's monotonically increasing. So it's always going to change. If this is an IP address field of a particular event type, then it will change based on the characteristics of an IP address string. So we can start building these rules into an engine without actually having to parse the individual data source types themselves, which is the lion's share of work when it comes to SIM integration. And as this is focused on the string structure and not the semantic content, we don't need to build any parsers anymore. So we're kind of calling this Zen parsing. Kind of, there is no spoon. But once we have this measure of closeness, we can then compare the logs coming from the same machine and then from other machines. And we are applying a combination of principal component analysis, support vector machines, and simple thresholding to actually do this classification. And we're clustering the assets based on multiple dimensions. So the obvious one is function. You know, is this a web server, a database server, DNS server, etc.? The second type of classification is role. Is this a server or a user endpoint as a coarse grain split? And it works out that based purely on net flow, our preliminary results are showing about a 90% accuracy rate for determining whether this device is a server or a user endpoint using no other additional data. The third type is variance. So how changeable is the asset's behavior over time? So as an example, does the variance itself point to further dimensionality? So things like an endpoint belonging to a finance guy. Typically, you'll see a large spike in activity of that user endpoint towards the end of the financial year. So can you use that to, again, subtype the classifications? And then finally, cardinality. So this is, in effect, the unique entries in a data set. So cardinality is defined, as I said, as the number of distinct elements in a data set. So some of the concepts we're coming up with now is the popularity or the promiscuity of a device. So how popular is a device or an asset? So for example, a vulnerability scanner is an extremely promiscuous device. It generates a lot of outbound connections to a lot of hosts. A DHCP server, for example, is a very popular device. It doesn't really generate many outbound connections, but we see a lot of inbound traffic to this device. So we can start asking questions like, show me the top 100 hosts based on the volume of traffic sent by the devices or to the devices. Show me the 100 least popular or the rarest domains visited today from my entire infrastructure and list the assets that made those requests. Things like port scanning become very easy to spot. They kind of light up like a Christmas tree because even if the port scanning is low and slow, because what we're doing is we're actually computing the cardinality over large periods of time. So a web server, for example, that may be responding to requests, so it's quite a popular device and a fairly low promiscuity score, if it's compromised and it suddenly starts port scanning its local network, over the period of 2, 3, 4 days, it will be very easy to see that increase in promiscuity. The problem with this is that measuring and reasoning about cardinality is computationally very expensive for large data sets. So this is where hyperlog-log comes in. So hyperlog-log is an algorithm for approximating cardinality. And it turns out for our use cases, we don't need to be 100% accurate for any of our use cases. Taking a statistical approach is sufficient. So the way hyperlog-log works is that if you take a hash of a value, that hash is pretty much random. And if you consider the binary representation of that hashed value, what is the probability of the last bit in that hashed value being 0? Well, it's binary, so it's 50%. How about the last 2 zeros? That's 25%. So as you go down, we actually, as these probabilities are now known, we can track their frequency and hence estimate the number of unique values in the set. So from the above, we can then estimate the number of distinct values. And we can also accurately estimate the known degree of error. So the smaller the hyperlog object, or the hash length, the larger the error. But it gets better. Hyperlog logs also support set operations, so we can do unions and intersections. So for example, how many new hosts were communicated with today based on yesterday's activity. So again, this would allow us to do things like detection of stealthy port scans, anomaly and outlier detection. It's well suited to MapReduce jobs, so we can both, it allows us to do parallel computing both for the creation and the use of the hyperlog logs. And as an example, a set of 1 billion unique IPs in a data set would basically resolve down to about a 1.5 kilobyte object with about a 2% error estimation on the counts there. So using traditional approaches where we're actually doing a full search through this data set, doing a distinct search, a distinct count search would take about 22.5 minutes on our cluster. But using hyperlog logs, we're dropping that search down to about 10 seconds, which means we can now use this concept of cardinality in many more use cases. So now that we've built this capability, what can we do with it? So some of the findings that we're looking at are, can we detect new log event types? Or can we detect a change in the mix of those event types coming from a device? And if we do detect a change, and it's a statistically significant change, could that be an IOC? Or is that some kind of a result of patching or some kind of other legitimate change and it's a change management process problem? So we can actually use this to detect unpatched assets. And we've been able to detect the difference between a 2008 and a 2008 R2 patched OS based purely on the log data coming out of it, without actually building parsers for that log data. The other nice thing about this is if we do have a known compromise, we can look at the delta between the known good and the known bad profiles, look at that delta and start looking for that same delta elsewhere in our environments. So we start building a pattern for how this compromise looks from a net flow as well as a change in log profile perspective. Another one of the findings is basically everyone likes DNS, but too much of a good thing can be an indication of compromise. And we've detected indications of compromise, and we've actually detected compromised assets based on their use of DNS as a side channel. The final piece is around topology and dependency modeling. So the nice thing about this is we can actually start building models of communication between assets and look at what is normal. Is it normal for a web server to talk to another web server? Well, actually not, based on the clustering and the typing that we're looking at. But it's much more common to see web servers talking to database type assets. It's very unlikely that user endpoints would typically talk directly to a database asset, but they typically talk to web servers. So we can start using the typing and the clustering that we're pulling out from this to start looking at pairings or communications that are anomalous in nature. The final use case is around credential use and abuse. So what we're looking at here is it possible to actually map credentials back to identities themselves? And it's fairly simple to do that when I have a one-to-one mapping in, say, my HR records. And it turns out that what a user should know and what a user actually knows are almost never the same thing. If I look at my systems of record, my AD and my LDAP, etc., I will have a certain number of credentials that I should formally have access to. But over time, that bleeds. I swap credentials with other people. It's just human nature. So instead of using the systems of record, we're monitoring usage records. And that turns out to be much more accurate over time. So a local authentication event, for example, would say, username X is logged in at time T, but a remote authentication would be something like username X logged in at time T from source Y, and Y could be an IP or a host. And what we can do with that is we can actually start stitching that path back together again. So in this case, our Unix admin guy, Ozzy Osbourne, is logged into his laptop, and then from his laptop, he then pivots throughout the day to multiple machines. And it's kind of obvious that this credential is different. I don't know if you could read that. In this particular case, it's a very simple pattern match difference. So using HR records, naming conventions for usernames, standard transforms, common account names, etc., it's really easy to take a first stab at whether this is determining whether this is bad. So this is fairly standard stuff. But the nice thing is that this works for any number of pivots as long as there is one and only one account logged into the asset at that point in time. So what about a more real-world example where we potentially have multiple users logged into the same box at the same time and then pivot using a more anonymous or a more shared credential such as root or administrator? So it turns out we can model this as well. So we can model the concurrent actors by basically adding weights to the relationships. So here we've got Ozzy logging into his laptop, Kim logging into her laptop, and then at some point in time, they both decide to log into this jump point. So they're both logged into the jump point, and now at some point, one of these two guys decides to pivot into an asset behind that jump point as root. I now can't tell. I've kind of lost the granularity there. I can't tell I can't assign the knowledge of that credential to Ozzy or to Kim. So we basically split the weighting. And it turns out that this ambiguity resolves itself relatively quickly. You know, Ozzy might take a day off, Kim logs in, I can now assign that. For simplicity, we've started with weightings of 1 here, but actually what we would do in the real world would look at the type of authentication that's taking place. So if this is single-factor authentication, maybe we weighted at 0.6. If it's two-factor, maybe 0.8, and we take it from there. So over time, we start building up a view like this, where the squares are basically identities and the circles are credentials. So we can ask some interesting questions to start with, things like excessive access. This guy at the top here, is he some kind of admin rock star and his role dictates the fact that he should have this many credentials? Or has the user moved around the organization and just retained credentials that should have otherwise been revoked? And again, we can start looking at this by typing the identities themselves by using things like the AD topology or the AD structures. So if this is a marketing guy, maybe you shouldn't have this many credentials. If he's an admin, maybe that's fine. The inverse is the obvious use case, the dot in the middle, excessive knowledge of a credential. So shared credentials are bad by default, so maybe this is a good candidate for a password rotation. And we can very easily generate top 10, top 100 lists of these kind of credentials based on sharedness. The other interesting piece here is what happens when an employee actually leaves the company. So now we can identify shared credentials that the employee had, legitimately or otherwise, as candidates for password rotation, so we're not going to lock anybody out. But we can also, with a much higher level of confidence, disable the unshared credentials. And finally, if you look at the authentications in the frequency domain, so you do a frequency analysis of the authentications, users tend to be fairly stochastic in nature. It's a nice maths way of saying they're kind of random. But if you compare that with something like a system type login, system logins are very periodic in nature. They're typically cron jobs, etc. Excuse me. So it's very easy to tell the difference. So within TELUS, for example, we have the concept of user accounts and service accounts. User accounts are typically all two-factor, and service accounts are used for scripted logins from between business processes and by definition cannot be two-factor, so they're single-factor. Admins being human beings, being lazy, etc., sometimes there's a bit of a tendency to use service accounts for logins. We actually were looking at building this use case specifically for that, to catch that use case. But it turns out that the inverse use case is actually way more valuable, where somebody has actually hardwired their own user credentials into a script, which is now part of a business process, and then they leave the company. And it turns out that operations teams typically are fairly hesitant to decommission admin accounts when an admin leaves the company because of this reason, because we don't want to break business process. So now we can detect that very easily. We can detect the source, dest IP, we can detect the credential that's actually in question. So, in summary, interesting data is everywhere. There's a fascinating realization in biology that you're just as likely to discover a new species in a tropical rainforest as you are in your own backyard. The thought there is that nature is so rich that it actually doesn't matter where you start looking. The important piece is that you start looking. So don't worry about, if only I could get agent X onto our endpoint so I could capture Y. Just really start with what you have in front of you. I guarantee you will find interesting correlations in the data sets you already have available to you. I believe a combination of stream processing and MapReduce type technologies are enabling analytics that were previously cost prohibitive. And ETL doesn't scale. MapReduce type technologies are actually inverting this paradigm. Instead of having processing platforms and ETLing data through them, causing delay at each point, this class of technologies is inverting that paradigm. We're actually bringing the compute to the data as opposed to trying to push the data through compute. And in my opinion, security analytics is actually more complex than many other big data domains. And the reason I say this is that we're trying to correlate multiple disparate data sets from thousands, if not millions of endpoints. And we're trying to detect actors that are typically actively trying to evade detection. So to do this, you really need tools that can reason about both log and packet data in the same engine. And this, I think, is a big failing of some of the tool sets that we have today. We have some fantastic SIM-type tools that specifically look at log data. We have some great network forensics tools that specifically look at network data. But we're really missing a trick. If we can combine those two and build correlation rules that allow us to reason about both types of data in the same engine, that will open up whole new use cases and whole new areas of visibility. And finally, the if-then-else type correlation rules are no longer sufficient. The level of effort to maintain a rule set increases exponentially as the rule set grows, creating a maintenance nightmare. So machine learning is key, preferably unsupervised learning, as a more effective way to make sense of these highly complex data sets. Okay, thank you very much. Any questions at all? This guy? Ooh. So this is a visual representation of all of the web traffic coming out of the TELUS corporate network for a day. So if I were to scroll into some of this, zoom into some of the stuff, you can picked Facebook straight away. Excellent. So you can see, basically the size of the node represents its connectedness, or the amount of connections to it. And the reason for this visualization was twofold. I talked a lot today about some of the kind of dry under the hood math stuff for how the correlations and analytics are being implemented. But really another area of work is how do we visualize some of this data? So an example of why we would visualize this kind of data like this would be stuff like this. So we would never detect this kind of data by looking at just lists of IP addresses and connections. So I'm not going to scroll in too much because I'd like to preserve the innocent. But you can probably read those IPs already. But what you see here is two IP addresses that were actually TELUS assets. And they were talking to IPs on the internet by IP, not by domain name. And there's this lovely star configuration where each of these machines was talking to each of these other external IP addresses. Nothing else in the TELUS enterprise was talking to any of these IPs. It's kind of jumped out like a sore thumb, and obviously these two machines were actually compromised. We have some other interesting examples. So things like, where are we? Maybe down here. So this is an example of a TELUS IP address talking to the Canadian Parliament. site, and this concerned me for a while, but it turns out that this IP address is actually connected to a machine that is streaming the Parliament video feeds to a call center. So the guys in the call center can keep up to date with what's going on in the Parliament. So that's an interesting one. Some other pieces here, things like, again, little islands of connectivity are always interesting. So looking at this guy here, so we see redhat.com and we see a bunch of IP addresses talking to those, to redhat.com, and these turn out to be our internal repo caches. So visualization is interesting. It's an interesting domain, and it'll help us when we're talking about trying to manage and wrap our heads around data sets of this size. I'm sorry? Well, those servers are connecting to the redhat.com domain to pull down new versions, absolutely, but they were a little island. There's nothing else in our environment that's actually talking to those things, talking to redhat.com. No, sorry, this is only outbound traffic at our edge. Yep. Any other questions? Oh, sorry, yes. Sure, yeah, that's an overlay based on some threat intel stuff. So it's more interesting domains that are being spoken to. Yeah. Possibly, yeah. I'm almost certain that's either Google or Microsoft. Let's have a look. Oh, it's horrible to read. Yeah, it's google.com. Sorry, bad rendering. So another view of this, which I think is also quite interesting, is so what if we, so the holy grail is, can I remove all of the, can I just only look at the good stuff, the bad stuff, sorry. Can I only look at connections that are going to something that is actually a malware site, etc. And that's actually really hard to do. And sometimes it's just worth flipping the question to say, can I just remove everything that I know is good? So if I can guarantee that this is good, I'm not interested in it. So this is an example of, again, same data point, same point in our network. We're looking at egress traffic to the internet from our corporate environment. But can we look at traffic to file sharing applications? So online file storage applications. So again, if I look at things like this, it should be fairly obvious that that's something like SkyDrive. We have the kind of iCloud collection of boxes down here. But again, if I look at some of these things, I'm starting to look at, again, an interesting relationship here where I'm seeing one IP address using 6 different distinct online file storage or file sharing applications. From our analysis of the full data set, it actually turns out that either individuals do not use online file storage, or they use more than 2 services. And the kind of sweet spot is somewhere between 2 and 3 services, about 2.2 services. So this guy is a bit of an outlier. Why is this guy using so many file sharing services from a corporate asset? So again, this is maybe an interesting one to investigate. Sorry, any other questions? Okay, I guess it's bureau.